So, in the last tutorial I have already taught how to implement a simple deep neural network and how you can back propagate through gradient descent algorithm, right. So, if you run that Colab notebook, you can check I have also printed the output after each hidden layer and the loss also. If you see the first epoch loss, you can get loss as 0.29, and next onwards I have also printed the loss for after 10 epochs, right, and as you can see the loss is decreasing. So, after 10 epoch the loss is 0.17, and like that if you see the epoch 20 loss, it is again coming down, right, 0.10. So, intentionally I have printed the loss only after 10 epochs. So, as you and I have also printed the output after each epoch, like as you can see the output H1 H2 out of H1 like that. So, I have also printed I think loss till let me check epoch 60, 70, so as you can see after epoch 190 the loss is very low, 0.003. So, for this exercise I have also run for 200 epochs. You can play with any numbers and you can see whether loss is decreasing or not. And for your reference, I have showcased the output of after each of the epochs and what is the output after the activation function, so on. There is one more thing you can notice. If you want to list down the parameters of the model after train, you can simply call model dot parameters, because now your model is trained. Now, whatever input or weight we started with, that got changed, because the now model has learned which weights needs to be updated, which one needs to be more, which one needs to be less. Like that you can see the tensor, which is the parameters weights, that is changed whatever we started with. So, we initialized with some parameter, now this is the final parameter after the model got trained, that you can get by model dot parameters. And if you want to simply predict, you can simply call model dot forward, and for the forward function you have to pass the input. So, for this example I have passed 0.06 and 0.12 as the input, then you can get the prediction. As you can see the final tensor 0.06 and 0.93. So, naturally 0.93 is too much higher. So, the predicted output should be 1. Now, one more thing you can note down, let us say you want to check or you want to tap some of the particular layer of some model. For this reference I have taken some vision language model, vision model. So, for that you can import this function like import torch vision as vis. Then under this vis package there are so many visual visual models. So, those are applicable for the images, you can list down. So, let me run that cell. Okay. While it is running, so you can list down the models by calling vis dot models. Okay. Then if you simply call directory of the vis models, you can get all of the things. Okay. So, there are so many models. So, under directory we will get not the model names, but some other parameters also. So, there are model like ConfNet, DenseNet, EfficientNet, GoogleNet, Inception, so many models you can get. Now, let me run it. So, as you can see, you can get vision transformer, so many models. Now, forget about these things. Now, let us say I just want to take the AlexNet model. What you can do? You can simply call vis models dot AlexNet. If I run it, you can now you already face the models AlexNet, then I have just assigned with some variable AlexNet. Now, if you simply print AlexNet, you can get the whole architecture of the AlexNet model. What it says? There is some sequential, there is some convolution layer, ReLU layer, max pooling. Those things you can ignore. These are the require for some image processing and some image vision model. Okay. So, like that if you change these two model to AlexNet to, let us say if you want to choose some other model like say ResNet, you can simply choose that. Okay. So, let me check where the AlexNet was. Yeah, this was the AlexNet model. Now, let us say I want to pick conv next, then what you can do, you can simply call visual models dot convnet, then it will be loaded. Okay. You can do this exercise. Okay. Okay, now, in this tutorial, this is tutorial 4, I will cover first word embedding. Okay. So, in this tutorial I will cover word embedding, I will cover implementation of recurrent neural network, and I will cover the attention mechanism also. This is the tutorial 4. So, you already know what to vec. So, you want to represent a word to some vector, okay, some multidimensional vector. So, let me start with this. So, you can import some of the important packages. So, for this exercise there is some corpus called Brown. Okay. So, I have taken some sentences from the Brown corpus. So, how you can get? You can simply download nltk.download Brown. So, for this you just need to install nltk package, and there is some package called gensim you can install, and you can get the sentences from the Brown corpus. Once you get the sentences, the sentences how you can get? You can simply put brown.sense, you will get the sentences. Then I have simply pre-processed the sentences. Okay. Now, I will just show you what is the output of the processed sentence. Just a minute, let me run this cell. Yeah. So, if you print the processed sentences, there are many sentences and I have tokenized into some of the words, right, as you can see. For example, this is one sentence, many changes involved minor editing and clarification, new point added. So, you can see each of the sentences now converted to into a list of words or tokens, right. Like that we have so many sentences. Now, if I want to print the what is the length of the processed sentences, you can simply call length of processed sentences. So, you have 57,000 sentences in the Brown corpus, right. So, each of the sentences now converted into a set of or list of tokens or words. And how you can do that? You can simply call this function. See, I have already taken the sentences. Now, if I want to simply we have just join for sentence in sentences, we have just taken list of the sentences and converted into list of words, right. Now, we want to train the word to vec model. Okay. So, this is very simple. So, under gensim package, from the gensim we have already imported the library word to vec. Now, if you want to train this word to vec model, you can take those processed sentences. So, these are some of the hyperparameters, like what should be the dimensionality of word vector. So, this I have taken as 100, you can choose anything. So, for some of the popular word to vec model, the dimension is 512, and here for the this exercise I have taken just to train this word to vec model, I have just taken the vector size as 100. Then you have to choose some of the context window, right. So, I have chosen the context window as 5. So, I can look 5 words before that particular word or 5 words after that particular word. So, maximum window size is 5, and there are some other parameters. Okay. So, there are two models, one is the continuous bag of words, another is the skip gram. Okay. If you want to train the continuous bag of words, then you can put this SG, that is skip gram equals to 0. If you put that as 1, this model will train the skip gram model. So, in order to train word to vec model, you have two options, one is the continuous bag of words and one is the skip gram, and by this parameter you can control that which model you want to train. Okay. You can simply run this cell, then the model will be trained, and you can save this model by model.save. Then let us say you want to find some of the similar words of, let us say, learning. Let me change it to learning. So, from the model you can call model dot wv means word to vec dot most similar, then you can put learning, then you can get some of this words similar to learning like wisdom with some similarity score like 0.97 and survival, extend, some of the similar words. If you want to get the vector of a particular word, you can simply call model dot wv particular word money, then you will get the. So, here I have for this exercise I have just printed the first 10 values of the vector, otherwise by default we will get 100, right. If you simply remove this slicing, if you print, you will get 100 size vector. Now, let us say if you want to check the vector, let us say for learning, you will get a completely different vector with 100 sized, right. So, after this training, each of the word now has converted into some of the higher dimensional embedding. In this example, it has been converted to 100 dimension. Now, it is very difficult to visualize 100 dimension, right. We can visualize still only 3D dimension or something like that, but in order to visualize in higher dimension, you have some method called principal component analysis. So, in this 100 dimensions, you can reduce it to some of the 2 dimensional space. You can simply project those 100 dimensional space into 2D space. So, in order to do that, I have just taken first 100 words of this corpus. As you can see, I have just taken the first 100 words by just colon 100. You can import the PCA package from the sklearn library, that is from sklearn or decomposition, you can import PCA. Then you can perform the principal component analysis. So, for here for this example, I have taken the number of components as 2 for the principal component analysis. Then you can fit that PCA method, and then you can showcase into 2D dimension. Let us see. So, for first 100 words, if I just want to project those words, you can see like this, right. So, now each word has been projected into 2D space. Now, as you can see, he and she. So, those are kind of gender, right, they are coming together, because if you print the vector of he and she, and if you calculate the cosine similarity between them, that would be higher. Okay. So, there is another method, so which also, that is called t-SNE plot. You can also try that, that is also very simple. So, the t-SNE package also you can get from the sklearn library. Here also you can put what is the number of components. This is the same way you can visualize, right. Yeah. Then if you want to save those word to vector, you can simply call model dot word to vec dot save word to vec format. You can either save in binary format, or you can put binary as false, then it will be saved as text. So, as you can see, word to vec vector dot txt dot get created. If you want to check it, yeah, you can see these are the for first 100 words. Okay. Sorry, I think it got printed for 25,000 vocabularies, and each of the dimension having 100. Okay. I think the number of unique words was 25,000, you can check it. Okay. So, here this is the word to vec embedding and how you can visualize. Next, I will move to recurrent neural network. Okay. So, in the class you already have understood the theory behind the recurrent neural network. So, here I will showcase 3 examples. First, I will show how you can predict the next character, that I am calling next character prediction through RNN. So, RNN is a sequence to sequence model. You can predict the next character, you can predict the next word, you can treat it as a sequence to sequence. Right. So, first I will show the next character prediction. So, for this I have taken the torch library. Okay. As you can know, you already know, you can import the torch library by import torch, and there is one neural network package which you can invoke by import torch.nnhnn. And for this, because you want to train the recurrent neural network, we need some optimizer that you can also import torch.optim as optim. So, for this exercise I have created a sample data set. Let us say your vocabulary is simply hello. Okay. Then you can convert each of the characters of hello into some of the IDs. So, what is your input or what is your input sequence? This is hello, and each of the character is first is H, then E, then L, L, O, right. And for H, because the next character is E, in the label or the output side we want to predict for the H E, but for E we want to predict L, for L we want to predict L, then for L O, then for O again the first character, that is H. So, in that way I have just prepared the sample data set, which is the input sequence and the corresponding labels, right. So, for each of the character now I have indexed into some of the numeric number, like you can see H has been now indexed to 0, E is 1 and L is 3 and O is 4. Okay. Then if you see want to check what is the corresponding, for 0 you can get 1, if you just put 1 you will get E, like that. Now, I am just converting these sequences into some of the tensions, because we have to work with tensor, right. For that reason I have just created x and y as a tensor by this prepared data function. Then you can print what is the x and what is their corresponding y. Now, in order to build the recurrent neural network, it is very easy. You can simply define some of the class. So, here for the simplicity I have just named that class as simple RNN. Then you have to take the nn dot module in this class. There for this model, for any of this class you have to build one init function and one forward functions. So, under init functions, so we need some of the input, like what should be the input size, what should be the hidden size and what should be the output size. So, in the init function you can initialize all of these. Then we have to initialize what should be the embedding. So, embedding is nothing but input size cross hidden size. So, whatever number of input and hidden you will take, you can simply call nn dot embedding. So, by default it will create some of the embeddings. Then for the RNN thing, in the under NN library, that is neural network library, you can simply invoke RNN package. You can simply call nn dot RNN. And what should be the input for that? Hidden size comma hidden size, right. And batch first equals to true means, so we have to batch, right, batch the sequences. Batch first equals to true means your first dimension will be the batch. Then we have some linear layer which is hidden size comma output size. Then under the forward function, you first you have to convert those input into embedding. So, you have already initialized the embedding function, then you can pass that input which is x to the embedding layer, then you can pass through the RNN layer. So, for in order to pass to the RNN layer, whatever embedding you have got like that x, you can pass through that RNN layer and the hidden. So, here I have some parameters like input size should be my vocabulary size which is H E L L O, right. So, we have only 4 unique characters, and hidden size I have just taken 2, output size is my vocabulary size, because I want to predict the next character, right. So, maximum possible unique characters I have to take as the output size as well. So, for this exercise, let us say I have taken number of epochs as let us say 500 and learning rate I have put 0.01, right. Then you can simply initialize the model. So, we have defined the class simple RNN, then we have already now initialize the sum of the hyperparameters which is required, which is input size, hidden size and the output size. Now, you have to optimize the loss, then you have to define some of the criteria. So, here I have taken cross entropy loss as my criteria. Then through some optimizer you have to optimize the model. So, now in order to optimize, you have to simply call some of the optimizer, which is I have taken Adam optimizer. You can pass the all the model parameters by model dot parameters and you can pass the corresponding learning rate. Then you have to run the training loop. So, for each of the epoch I have to create those embedding, I have to back propagate, I have to calculate the loss, I have to minimize the loss, done. Then once your training is done, for a particular input you can predict whether you can predict the next character correctly or not. Let me run it. Yeah, so I have printed the output for 50 epochs iteratively, first 50 epochs, then next 100, then 150, like that. As you can see, the loss is decreasing, right. Then if I give the input at HEL, what should be my predicted next character? It should predict L, right. So, this is the text sequence I have taken. Let us say HEL, let us say if I change it to, let us say I am giving it to, let us say HE double L, okay. Then what should be my predicted output? O, right, because hello, HELLO. So, for this small exercise you do not need 500 epochs to iterate, just I have showcased, because I am just printing for 50, after 50 epochs the just to showcase the loss is decreasing, okay. So, you can play with this. So, this is the next character prediction through RNN, it is pretty simple. Next, I want to move from that character space to, let us say, word space. Now, I want to predict the next word instead of next character. The same way we need the same package like torch package, you can import. Let us say I have just taken some sample text data, this is some random words I have just taken like hello world, hello PyTorch, hello RNN, next word prediction on PyTorch, just some simple random words. Then what you can do, you have to just split those words and you have to take what are the vocabulary, right. You can simply, this is the data preparation step. Then you can convert text into numerical tokens. If you want to see the data, you can simply print. Yeah. Then in order to build the RNN model, here I have just called it RNN model. You can simply first you have to do the embeddings, which is the vocabulary size comma embedding dimension. Then you can do the RNN layer, which is embedding dimension comma hidden dimension. Then at last you have some linear layer, right. Then in the forward function, first you have to pass through the embedding layer, then through the RNN layer, then you can return the output. So, here for the embedding dimension, for the simplicity, let us say I have taken only 10, hidden dimension as 50. Then you can train, you can take the for loop, you can, here also I have taken the criteria as cross entropy loss and the same Adam optimizer, right. So, I am passing all of the model parameters by again model dot parameters. For this example, I have taken, let us say epochs equals to 100, then you can simply train. So, as you can see here also, we started with loss 1.78, after each epoch the loss is decreasing, right. So, after each epoch we have to take what is the predicted word, if that is wrong we have to back propagate, we have to calculate the gradient, right. Then again we have to update those weights just to minimize the loss. As you can see, the loss is being minimized, right. After 100 epochs we are getting 0.3637. Then let us say you want to predict the next word. So, let us say I am giving some input as hello, I want to predict what should be the next word, then it is saying PyTorch, because in the text if you see, we have taken hello world or hello PyTorch. So, first you are copying hello PyTorch, okay. So, let us say I want to change the input word to, let us say PyTorch. So, once the model is trained, if you want to predict from that model, first you have to call model dot eval function. So, then model will come to the evaluation mode, not in the training mode. So, for that reason, when we are calling the predict next word function, we are first calling model dot eval, then we are saying that with torch dot no grad, because at the time of evaluation you do not need any gradient, because the model is already trained, you know what are the exact weights or parameters. Then you can pass that input word, what is the input word you can pass, then you can have to convert to the sum of the tensor, right. For that reason you are converting input word to sum of the tensor. Then the output you can simply pass that input word to the model, you can get those predicted ID, then you can convert back those predicted ID to word, because you want to visualize into words, not in the numerical numbers. So, let us see what it comes for PyTorch, coming hello. I think after PyTorch, yeah, after PyTorch it was hello, for that reason it is coming hello, right. So, let me change it to word. After word I am just expecting it should come prediction. So, let me change it to word and run. See, next word prediction for word is prediction, because in the sentence we had after word we have the word prediction. So, in this RNN implementation you have already shown how to predict the next character, how to predict like next word. You can convert into sequence to sequence also in this way. Okay. In this tutorial next I want to convert, I want to cover attention mechanism. Okay. So, now let us say I have a sentence, life is short, eat dessert fast. Okay. For this particular sentence, if you want to calculate the attention. So, first what I am doing, I am just converting the sentence into some of the words like life is short, eat dessert fast. Then I am just assigning some of the particular numeric number to each of the words or tokens. Then as you already know, you can simply convert into some of the tensor. So, now you got this tensor, because life, you see life is short. So, life is getting index 0, is 4, short is, I see short is 5. For that reason we are getting tensor as 0, 4, 5, 2, 1, 3. So, for this example I have taken like some sample, like some very low embedding dimension as 16. So, first I am just taking the embedding layer from torch.nn.embedding, this embed, because I have to embed this sentence, right. Then I have converted into some embedding sentence. So, for this examples I have taken, as you can see there is 6 words, right, 1, 2, 3, 4, 5, 6. Then the dimension of this tensor would be 6, 16. But in general, practically the embedding dimension will be higher. For this exercise I have just taken only some 16 number, some random number. So, first this sentence I have converted into some of the embedding. So, now for this sentence I am getting a tensor size 6, 16. So, this I am just giving some seed just for the reproducibility, each of the run you can get the same input. So, in the theory you already understood in the attention what is the query, key and value matrix, right. For the simplicity I have just taken some of the query, key and value matrix separately. Like as you can see I have defined torch.nn.parameter with some random query matrix, right. So, now my embedding dimension is 16. So, I have defined some of the embedding, some of the dimension for the query, key and value. As you can see dq, dk and dv, these are my parameters for the query, key and value dimension. Then once you define that, I have just defined some of the random query, key and value matrix, as you can see. Now, if you want to print some of the query matrix, you can see. So, this is my query matrix. So, the query matrix dimension is dq comma d, right. D is my 16 and dq is 24. So, this w query matrix you will get 24 comma 16. If you want to check, you can simply do w underscore query dot size. Yeah, you can get 24 comma 16, right. Now, let us say for a particular word, let us say I am just checking what is the, for the next word what was the embedding, second word, then you can simply check what was the embedding, right. This is the 16 dimensional. For each of the word I have just converted into 16 dimensional. As you can see for the first sentence there are 6 words, we have 6 comma 16 matrix. So, first the second word I just want to calculate the attention score. You can simply check the shape of this particular word, you can get the 16, right. Then for the second word we need the query 2. So, for the w query matrix under the w query, so for the x2 which is this embedding vector for that particular word, we just want to calculate the query 2. How you can do? You can pass that particular embedding vector to the query matrix. So, I have the w query matrix, you can simply matrix multiplication with the x underscore 2. Now, x underscore 2 is my second word's embedding. Then likewise you can calculate the key 2, you can simply in order to calculate the key, you have to pass through the key matrix for the region w underscore key, and I am just matrix multiplying with the particular embeddings. Once you calculate the query and the key, you have to again calculate the value also, then you can pass through the value matrix. So, like that I have calculated the query, key and value, as you can see. So, for the query I am getting the size as 24, key is 24 and value is 28, because I have already defined those query key matrix as the 24, 24 and 28. Fine. Once you get those, then you can calculate the, let us say you want to calculate the keys and values for each of the words. Then you can simply call matrix multiplication of the query matrix. You can pass the whole embedded sentence. For the compatibility of matrix multiplication, I have to transpose the embedded sentence. As you can see the W key matrix, you can see the dimension and you can see the dimension of the embedding sentences. Then you will check that for the matrix multiplication compatibility, you have to transpose that embed sentences. Like that you can create the keys and values matrix, and in order to get the particular attention score, you can simply call that query and you can dot product with that key matrix. For that particular thing, you have to just slice. For here I have just taken the fourth one, like that. Okay. So, this was some raw implementation. So, for better implementation like the scale dot product implementation, here I have also shown some of the function how you can implement the self attention function. So, this is the argument you have to take, this is the query, key and value. So, the query in practice you have to take the tensor size as like that, you have to take the batch size, you have to take the sequence length and the corresponding dimension, query and key. So, query and key dimension should be same, dk and dk for the reason I have taken, and the value matrix can be separate. Then you can calculate the dot product multiplication. As you can see, the scores is calculated as torch dot mat mul means matrix multiplication. Then I am just taking the query, I am just transposing the key. So, query multiplied by key, right. Then we are just dividing some of the, just for numerical stability, we are just dividing with some of the root over dk. This is the attention is all unit paper, you can see they are just dividing with some square root of the matrix the embedding dimension. Then at last we just normalize those score by the softmax function. For the reason I have just applied f dot softmax. If you apply this softmax function, you will get the attention weights first, then you can compute the output. So, how you can get the outputs? Once you get the attention weights, you have to multiply those with the value matrix. For that reason, the output you can get by attention weights and the value, then you can determine the output and the attention weights. So, likewise you can get the attention weights, this is the attention weights. So, we have taken some example input and output like batch size, sequence length and the dimension of the key and value. Then query, key and value you can define from those hyperparameters. So, here I have just showcased the how you can visualize the attentions, right. So, this is your query index and this is the key index, right, in the x axis, and the y axis you can query index. This color codes defines what should be the attention weights, right. More you can see the color code of the so from 0.0 to 0.7. So, 0.7 is like the color above the green one, you can visualize this thing. So, this also I have given some of the example for the sentences, you can check that. I do not want to invest more time here, then you can visualize the attention weights also. So, there is one more function just to visualize attention very clearly. There is very popular package called BART visualization. So, you can simply install pip install BART viz transformers BART viz, then you can simply use that BART viz package. So, the beauty of these things is, so let us say you have some sentence, the cat sat on the mat, you can give any input and you can tokenize those input by tokenizer.encode. So, from the transformer package you can import the auto tokenizer, okay. Then you can simply call that tokenizer, then you can get the attentions, then you can view, see, and you can, as you can see. So, if you change the layer, you can also change the layer also, then the visualization gets changed. So, each of the, in the transformer you have many layers, in the BART layer you have 12 layers. So, you can change. So, in each of the layer how the each of the words is attending to other words with how many weightages, you can just visualize that. This is very beautiful, right? You can see. So, this is the layers and this is the heads. Each of the layer, how is the attention is calculated, you can check. You can change this layer to 4, you can check it also. Okay. So, here I want to end the tutorial 4. Okay. So, I have covered the RNN word embedding and the attentions. Okay. In the next tutorial, I will cover some of the fine tuning task of some transformer. Okay. Thank you.